We will solve this today's LeetCode problem. The question is all ancestors of a node in a directed acyclic graph. So the question is marked as LeetCode medium. Let's see what the question is asking. So you are given a positive integer n representing the number of nodes of a directed acyclic graph. The nodes are numbered from 0 to n minus 1 inclusive. You're also given a 2D integer array, ages where age I is equals to from I to I denotes that there is undirected directional age from I to 2I in the graph. Return a list answer where answer is the list of ancestors of the ith node sorted in ascending order. Okay. So basically we have given a graph which is unidirectional. It means a directed graph, right? It is not a it is a undirected graph, right? It is not an undirected graph, it is a directed graph, right? So it is pointed to 0 to 4 only, source to destination. And basically we need to find the list of ancestors for each node and stored in the vector and return that, right? So what they mean by the list of ancestors means all the its parent as well as their parents also, right? That's what the ancestors means, that the node's parent as well as their parents parent and so on, right? So it means the node which has started from starting point to that child, to that node specifically, we need to find all the nodes which have started from the point, right? So if we see example, the first example here, this is the graph given, and if you see for zero's parent is nowhere, no, there is no parent of 0, right? So this is empty. Again for 1 there is no parent, empty. 2 there is no parent, empty. But for 3 can be reached from 0 as well as 1. So 0 and 1 both will be the ancestor for this 3, right? Again for 4, this 0 and 2 both the 4 can be reached from 0 and 2 both, right? So 0 and 2 are both of their ancestor, right? Again for 5, if you see 5 parent is 3, right? So 3 is a ancestor of 5, but 3 is also 3 parents is also 0 and 1, right? 3 parents is also 0 1. It means 0 and 1 is also an ancestor of this 5, right? Because you can think of like generation, right? That 5 father is 3, 3 is grandfather is 0, and something like that, right? You can see thing like that, right? The ancestors is something that, so 5 ancestors are 0 1 and 3, right? So 0 1 3 is our answer. Same for 6. 6 parent is 3 and 4. 3 parent is 0 and 1, and 4 parent is 2, right? So 0 1 2 3 4 all should be ancestor of 6. So that is the answer here, right? Again for 7, same thing. 3 and 2, or 3 and 2 both will be the parent of this 7, and 3 ancestors parent is also 0 and 1. So 0 1 2 3 all are the ancestors of the 7, right? So basically if we conclude the question, we need to find all the ancestors of all of each particular or of each node, right? So basically if the node has some parents, and if the parents has also, if the parent is also a child of, also a of some other nodes, then we need to then we need to include them all, right? Include them all, right? They are all ancestors of, all of them are all of them will be ancestors of this node, right? This current node, right? This current node. Okay, we understand the questions, right? So basically we need to just find all the nodes which are coming, from which this 5 can be obtainable, right? Basically we need to find that out, right? So the one thing is clear that the the immediate parent, the first, the immediate parent which we can form is can be obtained from this edge, right? The immediate parent can be we can obtain this from this edge, right? For 3 the parent is 0, right? For 4 the parent is 0. This is the immediate parent. For this 3 the parent is 1, and the same goes on, right? Same goes on. For 7 the parent is 2 again, right? 5 3. So this is goes on for the first parent, right? For the first parent, right? Now also need to find we also need to find its parent's parent, its parent's parent. Suppose this 4 parent is suppose this 5 parent is 3, right? 5 parents is 3, but 3 parent is also 1 here, right? 3 parent is also 1 here. If 5 parent is 3 and 3 parents also 1 here, so it means, and 3 parents also 0, right? This 0 and 1 both are parents of 3, right? So you can write it like this: 0 and 1, and remove this. You can write like this: 4 and 2, and remove this, right? Also for 6, for 3 also, right? You can write like this: remove this, 3 and 4. So if you see here, if 7 parent is 2 3, so 3 parents is also 0 1. It means 0 1 2 3 all are ancestor of 7. This is how we will find it. But how we will how we will how we will implement this? This we know that I need to iterate in all of the nodes for each of the nodes, that which parents is of which, and accumulate all of them and stored in vector, and for this particular current node, right? But how we will implement it? Basically the question is how we'll implement it. This is very uh, logical thing, that you need to move for each parents, and then from going to its parent value and store all of them parents in 7, and return that basically for each node, right? But how we will implement it, the main thing is there. So if you see here one thing, that it can that how we will start, from where we will start, from where will we start uh, finding the parent node, right? So if you see here one thing, the 0 parent is nowhere, right? 0 is 0 don't have parent, 1 don't have a parent, 2 don't have a parent. So it means if it does not have parent, and if it is has a child, if it does not have a parent, it means it can be the source from where it can be an ancestor, to all of the nodes of its children's or grandchildren's, of its children's or grandchildren's, right? Grandchildren's, or and so on, right? For sure, right? So on. So for this, if you see here one thing, that if I start from this zero part and include for its children and grandchildren, so I am sure of that this 0 will include in all of the nodes which should be included, because this will be an ancestor, because this 0 will be an ancestor for us, right? This 0 will be an ancestor. So if I start from 0, I can go to 3 and 4, right? So for going to 3 and 4, I can this 0 will be included in our ancestor for 3 and 4 all as well, right? So after this 3, I can go to 5 and 6. So for 5 and 6, this 0 will be ancestor, and this 3 is definitely be an ancestor. So the benefit of starting from the nodes which don't have any parent is that I am assured of that the children's which I can go from this ancestor will include this ancestor as in my answer. I'm assured of that, right? So, but basically, how will I how will I iterate? How will I know? How will I know that which don't have a parent, and what in what order, in what order we will see the nodes. The question is now here this. So basically, if you see here in what order we find. So if you see, we will move in that order, like the nodes which don't have a parent or less number of parents should come first, and then the nodes which has more number of parents should come at last. Why I'm saying that? The node which have less number of parents should come first, right? And the node has which has more number of parents more number of parents should should come later. Why I'm saying that? Because I need to include all the ancestors, right? I need to include all the ancestors. So if I start from the nodes which has more number of parents, suppose I have started from 5, right? I have started from 5. So it is a directed graph now. It is a directed graph. So how will I know that I can go to this 3 0 1 all are my ancestors, right? If I started from 3, I can know that this 3 can be a sister of 5 6, but how will I know that this 3 parents is 0 1, right? How will I know? How will I? Because because it is given a directed graph. It is a given directed graph. So I need to start from the nodes which has less number of parents, because I can move from top to bottom, right? I can move from top to bottom, right? Not bottom to top, because it's not a undirected graph, it's a directed graph, right? Because I in directed graph I cannot move back. In directed graph I cannot move back, although it is possible to move back, but that will take so much that we need to store parents and all, and then we can move back, right? I cannot move back without storing parents of each node, right? That's the precisely I can say that. So basically, what I can do, I will start from the nodes which don't have which has less number of parents. So if we see this example here, in this example here, this 0 1 and 2 has no parent, so this 0 should come first, this 1 come first, 2 come first, right? Again, now after this 0 1 and 2, after the 0 1 and 2, which nodes should come first? 3, 4, and then which nodes come first? Should come first? 3 and 4, right? 3 and 4, right? After this 0 1 and 2, this 3 and 4 nodes should come first, right? Again, after this 4, which nodes should first? 5 6 7. So 5 6 and 7. So if you observe it, it is same like topological sort. It is same like topological sort. If you don't know topological sort, uh, you can see that as a uh, that number of n degrees, right? Number of n degrees. We calculate the number of n degrees, and according to the number of degrees, we make the orders of topological sorts, right? Basically. So if you see for 0, how many degrees in degrees is there? So in degrees means the number of edges which comes towards the node. In degrees means in degree of a node means the number of edges, the number of edges which comes towards the node, right? So we need to calculate the number of nodes, so edges. So for 0 the number of edges is 0, 1 is also 0, 2 for 0, 2 is 2 for 2 is also 0. Now for 3 and 4, for 3 and 4, if you see here for 3 and 4, the number of edges is 2, because there are two edges coming towards 3, and same for 4 also. For 7 again, for 5 6 7, 5, then 6, then 7. So 5, for 5 again it is 1, for 6 it is 2, for 7 it is 2, right? So basically what we are saying, that we are starting from, in topological sort, we will start from the 0th in degrees, right? So if I start from 0th in degrees, so 0 1 and 2 will be come first, 0 1 and 2. After this removing from 0 1 and 2, this edges, if I remove from this 0 1 and 2, this edges will also remove from here. So if this edges is removed, so 0 1 is removed, so for these three, both edges are removed. So after removing the node 0 1 and 2, edges will also be removed, right? So if edges will remove, this three will edge, this three edge will moves to this three, two number of edges move to 0, right? Same for 4, this 0 removed, 2 removed, so 4 edge number of edges should be also 0 now. And for 5 6 and 7, so 7 has two nodes from 3 and 2 is removed, so 7 edges also changes to 1, right? 5 and 6 no touched, right? Now this 0 and 2 removed because we have already included in our answer. Now which node has 0 edges? 3 and 4, so 3 and 4 should be in order, right? I can either you can write 3 and 4, or you can write 4 and 3, both is correct. Because topological sort can be in any order according to the index. Either you can write 3 and 4, or you can write 4 and 3, all both is correct, right? Both is correct, right? So 3 and 4 would be there, right? If I remove 3 and 4, I included 3 and 4, so I will remove it. After removing this 5 6 and 7, all edges will be removed. So after this 3 and 4, this 1 changes to 0, and this 2 changes to also 0, and this 7 also changes to 0, right? So 5 6 and 7 both all are in 0, so we can include that. So this becomes 5, then 6, and then 7, right? So see, this order and this order is same. This order and this order is same. It means we will we need to take help of we need to take a help of topological sort topological sort for finding the ancestors of each node, right? So how will it help? So if I suppose I started from zero, right? And from 0 1 and 2, this is the order of starting, right? So from this 0 1 and 2, from this 0 I can go to 3, I can go to 4, right? From 1 I can go to 3 again, and I can go to 4 also. So when I include this 3 and 4, for this time 3 and 4, this 0 and 1, both parents can be, both parent is for 3 and 4, right? No, sorry, for this 4, the 0 and 2, for this 4 0 and 2, for 0 and 1 it is 3 and 4, and for 1 it is only 3, not 4, right? For 2 it is 4 and 7, for 2 it is 4 and 7. So if you see, for 3, 0 and 1 both is a parent, right? Both is a parent. And I know that 0 we have started from 0. It means if I have already included this 3 in this 3, this 0th part, right? If I already included this 3 in 0th part, so I can check that whether this 0 has already a parents or not. So it doesn't have any parents still, till that it doesn't have any parent, right? Till that it doesn't have any parents. So this 3 will only store, this 3 will only store. So basically I will write it here, this 3 only have 0 parent, right? So basically it is a node to parent mapping, and this is node to children mapping, right? So we will use this for finding this, right? Basically, so for this 3, 0 is a parent, and for 4, 0 is also a parent, right? Now we will check, when we got 0 for this 3, I will check for 0 that do we have any parent for 0 right now? No, we don't have, right? We don't have. So we will don't do anything, right? Again, for when we come to 1, this 1 has children 3, right? So it means 3 have also a parent of 1, right? So I will include this 3 as a 1, right? So I will also check that whether this 1 has some parents or not. It just doesn't have any parent. It doesn't have any parents, right? So we will not include in this. So we again go to 2, and its children are 4 and 7. So 4 parent will be 2. Also 7 parent will also be 2. we will again check for 2 that whether 2 have as a parent or not. So if you see, we haven't got any parent for till for 2 right now, right? Now the thing is, we move to 3 part, right? Because this will be this will be arranged in this order: 0 1 2 3 4 5 6 7, right? So we will move in this order in the nodes, so we will check in this order only, right? So 0 1 and 2, now 3 will come, right? So this 3 will check. This 3 nodes is 5 and 6. This 3 node is 5 and 6. So for this 5, when we include this 5 node is, this 5 parent is now 3 for sure. And when I include this parent as 3, I will check for 3 that which parents are associated with this with this 3. So yes, 3 has some parents which are the is 0 and 1. So I will include this 0 1 with me also, right? I will include these parents with me 5, right? Same for 6 also, because 3 children is 6 here, right? So for 6, I will include 3 as my parent, 3 as my parent. Also, I will check for 3 that which parents is associated with 3. So 0 and 1 is parent of 3. So I will include both also, right? Now, this 5 and 6 is over, right? This 5 and 6 means 3 three children are over, right? So now we will move to this 4 part, because this is the order. So I will move to 4 and I will check which has children of 4. So if I see the children is 6, right? It means 6 is the children, means 4 is a parent of 6. So I will include 4 as a parent. When I include 4 as a parent, I will again check that the 4 has some parents or not. So it has a parent as 0 and 2. So 0 is already included, so there is no need to include again this 0. But 2 is not here, 2 is not included here, so we will include 2 here also, right? 0 is already included now, so we will just include 2 here. Now the 4 children are over, right? Now I will move to 5, because the order of topological sort is this is the order of topological sort, and we will move according to that only. So when I move to 5, it has no children. It has no children, right? It has no children. So nothing needs to be right. It right. These have no children. So we will move to 6. It has again no children. So nothing needs to be there. If I go to 7, nothing needs to be there. So if you now see here, if you now see here, this 7, if you now see here, this 7. Okay, sorry. One thing I missed something. Right, for 3 there is also children 7. In this 3, this 7 is also children, right? I missed something doing right, and that this 7 is missed. 7 children is also there for 3. So I will need to include 3 as a parent. Also I need to check that 3 has some parent 0 and 1, so I also need to include, right? So now you see here, we have all the parents, we have all the ancestors, we have all the ancestors mapping. For 0 there is nothing, for 1 there is nothing, and for 2 there is nothing, right? And if you see in the answer, 0 1 2 empty, 3 had 0 1 4 0 2. And one thing is here noted that list of ancestors should be sorted in ascending order. So after completion of the ancestors for a particular node, I need to sort it, I need to definitely sort it. So I will sort it after just including or the ancestors from their parents also, right? I will just sort it. So basically if you see here, what we are doing, what we are doing that just we are we are finding the order of nodes traversal using topological sort, right? Using topological sort, right? Then we are we are traversing the nodes graph. We are traversing the graph from uh, in the orders, and find and fetching all the and getting all the finding all the sorry for the English, for finding all the ancestors, all the parents and ancestors, right? Parents, parents and ancestors for that of their children's of their children. Right? So what we are doing, we are moving to each node, then we go to its children, right? We are going after in order and move to its children, move to its their children, and then we are making the parent that node. Then we are also moving to its parent ancestors if it is present, right? If it's present for this children, right? So basically we are doing that, right? So now the part is the now the second thing is how we will implement this. We have done the logic. The implementation part is on you, that how will you implement. I will show you that how can I implement it. Just uh, so also uh, just take the just we will see the implementation now, right? We will see the implementation now. You should try implement now, that you first need to topological sort and find the order. Then you move in the order of nodes and find all the children's. Just I have done this. And for each node, this this is the parent, and move. If its parent is also available, then we will move also include that and sort it before inserting in my final answer, right? That's we will do. Let's try to just implement it. And let's just try to implement it. There are many things. Let's just try to implement this. So this is something we need to include. Now the first thing is we need to find the order using topological sort, right? So basically, for finding the topological sort, I need in degrees. So I will find in degrees of all the nodes, right? I will find in degrees of all the nodes. So basically I will iterate in ages and count. So in degrees is that the number of edges coming to towards node, and 0 3 means from 0 to 3, right? From 0 to 3. So basically in degree is e1, right? This is the in degree, right? And I need to store according to that only, right? Also I need to make a adjacency list to find the immediate parent of all the nodes. So that would be vector adjacency, and right. And what I will do, I will just store all the immediate parent of all the nodes, like that, right? I will just store all the parents, all the childrens of the particular node according to that, because ultimately I need to move in parents, right? Ultimately I need to move in childrens to find all the ancestors of the particular children, right? Of course. So what I've done, I have just stored all the integers of all the nodes, and also I make a adjacency list, right? Now I will need to use topological sort. So for that I need to take a I will apply bfs on that. So, for which are the nodes I need to insert initially? The nodes which has in degree 0, right? Because it is it is a directed graph. So those initially the nodes which don't have any parent, its in degree will be 0. So I will insert all the nodes whose in degree is 0, right? So I will insert all the nodes whose in degree is 0, right? So basically, it's just an implementation. How will you implement the question, right? So basically, we will insert all the nodes which has in degree 0. In this example, 1, 0, 1, and 2 will be the nodes which will be inserted initially. Now the question. Now, what I will do, I will iterate in this Q data structure, and what I will do, I will move to its children. I will go move one by one the nodes which is in Q data structure and move its children, right? Move in this children, right? Okay. So one thing is here, that when we are moving, so what we will do, we will just move in x adjacent node, right? This will be the node. So this is the adjacency node. So this adjacency list has a node which has a children. Basically we have done this here because this is from and this is source, right? So this is source to destination node, right? So this is the source and this is destination. It means the node which is on the adjacency must have this children. So this children, we will see this children, right? We will apply some condition on this children. So what do we need to see? So basically I need to store ancestors for these children. So for these ancestors, what I will do, I will take an extra data structure or array of sets which denotes n, right? Which denotes n. So what it will do, it will just it stores all the ancestors for this particular node, so this x is a children. If x is a children, this node will be our parent. So insert I will insert this node as my parent for this x, right? Also, one thing I have told you, that if I'm including this here, if i'm including if I'm including for this 4, make this parent as 2. So I also need to check 2's parent, right? Whether 2 has any parents or not, right? Whether 2 has also parents or not. So I will check for that, whether 2 have any parents or not, whether 2 have any parents or not. If 2 has any parent, I will insert them also in my vx, right? I will insert them also in my vx. So that's how I will store all the ancestors for this x children, because x parents is node and we are also fetching the node's parent, right? So this is how we will fetch all the ancestors. And why I have taken set? Because if you see here, in this case if you see here, uh, yeah, in this case if you see here, this 7 node, this 6 node is included 0 1 3 4 2, and 0 will come. It can be possible that some of the nodes originated from the two same nodes, right? So if I don't take insert set value, it can give me duplicates nodes for that, right? So that's why I have user set. And also I need to insert all the ancestors in ascending order, na? So this set will give me all the nodes in ascending order. So there are two benefits of using set. There are two benefits of using set. The first is the first is it it will give me distinct parents, distinct ancestors, distinct ancestors. And the second benefit is it will give me in sorted order. it will give it will give me ascending order, sorted order, all right? Sorted order, right? Give me ancestors in sorted order, right? So this is the two benefits of using set for each node, right? And after that, what I need to do, so this is basically x nodes. So after that, also this node is already taken. So this needs to be deleted in sorted order. So if it is deleted, so its age will also be neglected for this x. So for x, the in degree will also be reduced. The count of in degree is also reduced, because if the 0 1 and 2 is removed, so this age will also remove for 3. So 3 age removed, so this in degree will also reduce. So I have decreased the in degree. Now I will check whether this in degree of x is 0 or not. If it is 0, then I will include in my q data structure to make further operation on this node when it comes to here, right? So that's how this is uh, working here. And after that, after this loop over, I'm sure about that this node has all the ancestors. This node has all ancestors. Just I need to uh, change its data type from set to vector, because ultimately I need to return in vector, and I have taken vector set. So I need to change it from vector set to vector. So what I will do, I will take another extra space. For that, let's take as answer, and that will be n. And I will just iterate from 0 to n, from 0 to n. And what I will do, I will find all the ancestors which is present in this set, right? So what I will do, I will move in this set, which is v, right, which is v. So this would be x, and this is vi. So this x will have all the this x is an ancestor which is in a sorted order. So I will just need to store this in my sorted order, pushback x, right? This I just need to do, and I will just return answer from here, right? So this is how we will solve this problem. Basically, what I have done, I have used a topological sort to find the order of the nodes so that I can iterate. And basically, why I'm doing topological sort, because it, how will I know that which node has their ancestors of what, because it is a directed graph now. So it is, if it is a directed graph, I cannot reverse back to its parents. For that, I need to restore its parents. So instead of that, I will just store all the nodes in order, at 0, 1, 2, 3, 4. This is the order of their parents, their top parents, the top root of the graph. And I will traverse till their children's, and include all the parents for that children. So basically, I've used topological sort for that, and include its parents and its parents parents also, right? And I'm sure about that this has include all the ancestors, because I have started from the top elements, right? So this is how we will solve this problem. I just included all in the answer. Let's try to run this, and whether see that I have uh, stored all the numbers in my order or not. So we have passed the sample case. Let's just submit it. So let's see if we have passed all the cases. We have successfully passed all the cases, test cases. So if we include the time and the space complexity, right? If I see the time and the space complexity for this problem, so basically the first thing we have done is we had iterating in ages. That would take O of m, definitely, right? The number of ages is m. And also I'm iterating again in whole of n for insertion of initial nodes. So that will take again O of n, right? Again, I need to iterate in this queue. Again, I need to iterate in this queue. So for iterating in this queue, the one thing is that all the nodes would be definitely be iterated, right, till it is not empty. So O of n for that also I need to also move in this all nodes children, right? I am also moving in all nodes children, and also moving in children's parents parent. So basically, what is done, this n node and this node is moving again and again, right? It's basically moving again and again. So for finding topological sort, this is O of n plus m, right? If it is, this is O of n plus m. And also uh, for finding the its parents, I need to move two times, right? I need to move two times. So basically, it can possible that I'm moving the same node, same nodes again and again in the worst case. It can be also possible that when I'm moving for this node its children, and this children, this parents can also be treated again and again. So that will that will definitely take O of n square. That can take O of n square in the worst case, right? In the worst case. And also, one thing is here that when I am inserting this vx in my I, so it can be possible that all the nodes are inserted for a particular node. So that is for and the set takes log of n for insertion. So that can take O of that can take O of n square log n, because there can be possible that for a single node all the nodes are inserted for this single node, right? So for that, that can possible, and that will be O of n squared log n, because they are total n nodes. So it can be possible that the time complexity would be O of n squared log n for this Q data structure, right? And again, I need to move for this n and store all the nodes for this. So that can also take O of n squared, right? That can also take O of n squared. So basically, it's, if you observe here, so that would be O of n squared log of n, log of n, plus O of m, because this n and this is bigger, so we will take O of n square log of m plus this f O of m, right? So this is bigger, so of n square m plus O of m. This is the time complexity, and the space complexity would be, now the space complexity is also much further, because one thing is we have taken in degree O of n, again adjacency list, so that will take that can take O of n squared also, right? And again the Q data structure, so that would take O of n again, and again the set, that can take O of n square again, and answer O of n square again. So ultimately either it is O of n plus O of n square. So ultimately you can write it like O of n square, right? So n of n square would be the space complexity for this problem, right? So this is how we'll solve the problem, right? And this is the space and time and the space complexity for this problem. So basically it's just a topological sort. If you know the topological sort for the directed graph, which I have already also told you in this video. So hope you understand it. Hope you understand it. Hope you understand it. And if you don't, please write it. Please write it. That will help me. Right? That will definitely help me to uh, to know that whether you are understanding or not. Whether you are understanding or not. Right? Whether you are understanding or not. Right? So thank you so much. Bye bye.